Hello, my name is Jeremy Speth, and I'll be presenting work from Notre Dame on non-contrastive unsupervised learning of physiological signals from video. As the heart beats, there are very small color changes and movements in the face that are detectable in RGB video. If we pass a video through a neural network, we can actually directly infer this pulse waveform. But typically, this requires supervised training. So we collect data from, say, a fingertip oximeter and synchronize it with a video and train the model on that waveform. But collecting this data is usually very hard and limits the sort of settings in which we can collect video. We present a method that exploits the sparsity of the pulse signal, since it's a strong periodic signal. It also only exists within a finite bandwidth, say 40 to 180 beats per minute. We come up with a method that can actually directly train models with just video and no ground truth. Before we get to the approach, let's further motivate why we're pursuing camera-based vitals. Contact devices have several downsides. Many of them are quite expensive, and a lot of them only extract, say, one particular vital sign, like a blood pressure cuff. They're also quite uncomfortable. The blood pressure cuff, say, squeezes your arm quite hard. And most of them, aside from wearables, are quite infrequent. So you're only getting these physiological measurements, say, once every week, once every month, or only at the doctor's office. Cameras offer a nice solution in the fact that they're cheap. They're in many devices already, like our laptops and mobile phones. And they can actually, just from video, you can actually extract multiple different vital signs, such as respiration, pulse rate, and there's even recent work on blood pressure. Here's an example of rPPG, or remote photoplethysmography, which is extracting the blood volume, which is what we pursue in this paper. So in the top plot, this is just estimating the pulse with a 3D CNN from the video. And in the bottom, this is the actual ground truth recorded from a fingertip oximeter. We can see that the frequency and the estimate from the 3D CNN is actually quite accurate. Going back to some of the problems with this, however, training these models usually requires supervised learning. So we have to collect these large data sets with simultaneous video and recording from a fingertip oximeter, and they need to be synchronized. This is actually quite challenging, and it sort of restricts you to a lab setting in which someone's tethered to a machine. So the solution that we explore in this paper is actually unsupervised learning. So can we actually learn to predict the pulse and extract good features just from unlabeled videos? There's some previous work doing this, but it's all using contrastive methods. So they assume, say, videos from two different people will have two different pulse rates, which isn't always the case. A lot of people have resting heart rates that lie in a very similar frequency range. Um, and this could potentially lead to problems during training. Some of the assumptions here aren't always correct. Our method, which we call sync, signal estimation via non-contrastive learning, we're really exploiting some prior knowledge we have on the problem. So if we're looking for periodic signals like the blood volume pulse, we know that if you look at its frequency content, it's actually quite sparse. So there's a very strong periodic component, which means that very few frequency values are usually occupied. And we also know that the sort of domain is restricted for these signals as well. We know that a pulse rate shouldn't be, say, 500 beats per minute, and we're not going to find that in our data. So we can sort of penalize the model for predicting frequency content outside of, say, 40 and 180 beats per minute. And we use three different losses here. So the one I just mentioned, bandwidth, so penalize power outside of 40 to 180 beats per minute. We also look at sparsity, so we encourage the model to predict most of the spectral power near whatever the spectral peak is that it predicts. And then lastly, we add this component which encourages batch-wise variance. So we know that if we gather a large batch of videos, the pulse rate shouldn't be exactly the same for all of them. So we sort of encourage the model to explore the range of frequencies on this finite support that we allow. And all of these losses are performed in the frequency domain. So our model predicts a waveform, and then we convert it to the frequency domain with the fast Fourier transform. Here's a look at the different losses. If you train a model with, say, just a single loss, say the bandwidth loss, so this left column here, the top rows are just a single sample, and the bottom row is the sum of the power spectral densities for the entire validation set. So for bandwidth, if we train a model with just the bandwidth loss, it'll stop predicting spectral power outside of 40 and 80, 100, or 40 and 180 beats per minute, but the solutions aren't sparse. So you can see there's this sort of error here in the predicted waveform. For sparsity, it'll actually converge towards predicting very sparse solutions, but they're very low frequency signals that the model predicts. And this is not the correct signal. It's not the pulse. And with variance, the model actually predicts very wideband signals. So it covers a large portion of that, but it's not sparse. But if you combine these by simply adding them, our model actually converges towards finding the correct pulse signal. And it sort of predicts just a sinusoid because that's a perfectly sparse solution in the frequency domain here. We experimented with 3 different rPPG datasets. So this has ground truth pulse rate data, so DDPM, pure, and UBFC. And we also trained a model on, for the first time, on a non-rPPG dataset. So this is just a dataset that has no pulse ground truth, but we train models on it, and then we can evaluate those models on these rPPG datasets. And we do find that training on this HKBU Mars dataset, the model can successfully transfer to, say, UBFC and pure afterwards. Here's some more examples of results on the three rPPG datasets. So the top UBFC, middle here pure, and the bottom DDPM. We see that the model ends up predicting somewhat close to sinusoids, but it's the correct frequency. One thing is it learns its own phase because we can't have any prior information on what the phase should be. And overall, the mean absolute error for the beats per minute prediction on UBFC and pure is less than 1. And this method actually competes with supervised methods as well. Thank you for listening to our talk. We have code available for this work on the link here, and I'll be presenting Wednesday afternoon.